use the pad. Second.
So, Wang Xiao, can you share your screen?
Yeah, just 1 second. Just 1 second. I'm
okay.
working on it. Yeah.
Okay, I'm just checking out that everything is okay.
Okay. Okay. Yeah. So I'm sharing it from another pad. So I guess you all should be able to see it. Yep. So today I'm going to talk about a different type of zero knowledge proofs that that is kind of different from what the people not commonly see from public sources. Okay, so this kind of zero knowledge proofs is so-called designated verifier zero knowledge. I'm going to talk about what it means, what's the benefit, what's the disadvantage and advantages of it. It gives you many unique features, and one of the interesting features is affordability. I'm also going to talk about exactly what that means, but like how affordable, what does it mean by affordable very soon. And finally, I will talk about how it can actually be used to build scalable tools for machine learning tasks. Okay, and like if you have any question, you can always feel free to interrupt in the middle. It's like we can make it interactive. Okay, so so zero knowledge proof, or in general, zero knowledge proof of knowledge is or maybe like before I start, I'm I'm not sure about the background in crypto for this audience, so I will try to go a little bit slow, and in terms of the basic concept, I will try to cover a little bit more in terms of the background. If you feel like I'm going too fast or too slow, you can also you can always ask me questions in case there are part that you don't understand. Okay, and so zero knowledge proof of knowledge is a particular type of popularly regarded as zero knowledge proofs, in the sense that it's usually defined to be a more composable construction. So it's composable means that it usually satisfy more requirement than ordinary zero knowledge proofs. For example, in normally when we talk about the knowledge proofs, we will talk about we are usually 3 properties, right? The first property is completeness, meaning that if both parties are honest, then the verifier should be convinced. Okay, so essentially, if both parties are honest, then if X satisfies some predicate, then the verifier is going to be convinced. Okay, this one is fine. Okay, the second one is zero knowledge, meaning that if even for a malicious verifier, the malicious verifier won't be able to figure out any other information except for the fact that the predicate is satisfied. Okay. This one is also fine. Okay, this one is mostly fine. Okay, but the third one is somewhat is like the tricky one. Okay, so the third one is usually often refers to soundness. Okay, so there are at least 2 versions. Okay, so at least there are 2 versions that are practically relevant. Okay, so the first version is the normal version, which is if we use English, it will be if the prover does not have X, then then there is no way for the prover to convince a honest verifier that the predicate is satisfied. Okay, so if let me write it out. If a prover does not have X, then the verifier is not convinced. Okay, I mean, this one is probably maybe most people who have not studied the cryptography knows. Okay, so if a prover does not have X, then verifier is not going to be convinced. Okay, however, a stronger version of zero knowledge proof, which is there are different versions to frame it, would be something more explicit. So the second version says that if a verifier accept, then there exists a extractor that can extract X from the prover. Okay. The second version is explicitly stronger than the first one because if you take the control positive on the first one, it means that if verifier accept, then prover knows X, but it doesn't say exactly what does mean by prover knows X. And here, like the second version said, there exists an extractor such that it can extract X from the prover. So it must contain a explicit procedure to extract the witness from the prover. And well, I mean, I don't want to go into that much detail in terms of what I mean by extractor, but I just wanted to emphasize that there are two versions of zero knowledge proofs. Okay. So there are many. Well, so the definition is somewhat complicated if we really want to get the rigorous definition, and there are also many different kind of approaches. Okay. Well, there are succinct zero knowledge proofs, non-succinct and non-interactive zero knowledge proofs or argument, or like snacks or their variations. There are IOP-based protocols. There are, for example, GKR-based protocols. There are, for example, like protocols based on the idea of MPC in the head, and so this one is like 2007. This one is like 2013, and these three are like has like a longer history. Okay, and MPC in the head is also non-interactive, but the last one, which is zero knowledge proof based on garbage circuit, is almost often interactive. Okay, so like it could be made non-interactive by paying very high cost, but otherwise like a zero knowledge garbage circuit is interactive and cannot be made non-interactive. Okay, that's the very important part. It cannot be made non-interactive. Okay. So I talk about all these different kind of approach. So like we can actually classify all these types of protocols with different kind of properties. Okay, some of them like have been kind of studied a lot, and some of them have not been paid a lot of attention because of well, I guess historical reasons. Okay, well, the first one is interactivity. Okay, whether a zero knowledge proof is interactive or non-interactive. So the non-interactive would mean that the prover just need to send one message, so one message to the verifier, and then the verifier can do a local computation and like output whether it accepts the proof or not. Okay, the interactive zero knowledge proofs is going to be a process that involves multiple messages between the two parties. Okay, so prover sends some message to the verifier is going to do some computation and then return another message, and then the prover sends another message to the verifier. Okay, and then back and forth. Okay, so some interactive zero knowledge proofs can be made non-interactive using different techniques, but not all of them can be made in non-interactive. Okay, so I mean, ideally we want non-interactive zero knowledge proofs because it's it's like the message can be reused, for example, and many verifiers can verify it. So non-interactive is good, but not all of them can. Not all of the existing protocols can be made non-interactive efficiently. Okay, so that's like interactivity. Okay, any question? Okay. So this is in terms of the run of communication, and we also have we are also interested in the succinctness. Okay, this refers to the amount of messages or the amount of communication between the two parties. Okay, we have for example succinct like proofs. Let's say it has say like a constant number of communication with respect to the circuit size, or logarithmic to the size of the circuit. Well, I guess like whether it is called succinct or not is like I guess like it really depends on the definition, but but the size could be logarithmic to the circuit size. And some more succinct would, for example, could be something like square root of the circuit size, and not succinct would be like linear to the circuit size. Okay, yeah, I don't know any protocol that actually need super linear communication. That would be, I guess, like maybe quasi-linear is there may still be protocols with quasi-linear complexity, but super linear would be kind of surprising. Okay, but we also, so in terms of circuit size, we have like a kind of also a full spectrum from very small communication to very high communication. Okay, so these two have been studied a lot. Okay, mostly in the context of SNARK and other related protocols. Okay, so the third one is efficiency. Okay. So in terms of the efficiency, I usually categorize it into kind of 3 levels of operations. Okay, so the first one is about protocols who need linear number of public key operations with respect to the circuit size. So essentially, like let's say we have a circuit, a set of constraints, then it requires a constant number of public key operations for each constraint or for each circuit. Okay, so public key operations are usually not very fast, and it could lead to odd even kind of hassle. For example, you want to be constant time program, you wanted to have different properties. So this one could often lead to very heavy computation. Okay, the second level would be we want to run a FFT or NTT number theoretical transformation on the whole circuit. Okay, so the first one would be the complexity would be C times the cost of public key operation. Okay, the second one would be C log C number of basic operation. Okay, so because of the cost of the NTT, so there is a logarithmic factor, but it's a C log C number of a basic operation. Okay, basic. Well, the first one is C number of public key operations. Okay, so in practice, in terms of the computation, this one is usually faster than the first one in terms of the cost, because public key operation is asymptotic, the number of basic operation involved is often more than log C for a reasonable C. Okay. Well, and I mean the ultimate one, we would want a C number of basic operation, which means that we just run very cheap operations for each gate. That would be the best. Okay, that would make everything as fast as possible. Okay, but it's not clear whether it is how to design it to get the best of every aspect. Okay. The next one is trusted setup. Okay, so this one is actually somewhat related to some of the previous the definitions that I talk about in terms of proof of knowledge, and we also for now usually there are 3 types of trusted setup. Well, the first one is no trusted setup, which is the best. Okay, one way to classify would be whether the trusted setup is usable for every program, or is usable for just one program, and for the next program you need to reset it up. Okay, so for example, some of the classical snarks requires a per program setup. Okay, another spectrum would be whether the trusted setup is structured or not. Okay, because if it is a structured setup, then you would need to use a ceremony to run it, because I mean, you have to make sure that the secret is not owned by anyone. Okay, but if it is an unstructured setup, for example, which is indistinguishable from a random group element based on DDH, then it's much better. Then you just need to agree on some random beacon, so it's much better. Okay, so this is the best would be does not have trusted setup. Okay, so the first 4, I think if you've been following zero knowledge a lot in terms of especially in industry, maybe the first 4 are kind of familiar with you. Okay, but the last one is probably not as well known or well studied, or has not paid as much attention as compared to the first 4. Okay, so the memory requirement. Okay, so in order to illustrate it a little bit better, let's think about ordinary program. Okay, let's say I can run a program for a day. Okay, and the memory usage could stay the same. Okay, so although the program runs although the computation continues, the amount of of memory that is used by the program does not increase as the program runs longer and longer. Okay, that's kind of everybody is kind of is very used to it. Okay, so the task of the computation becomes the task that we compute becomes larger and larger, while the memory usage is not does not increase as like in terms of the running time. Okay, so that's like people like I believe everybody like is fine with it. For example, I'm using Zoom right now, and the Zoom just use like a stable amount of memory. It doesn't use as like a more memory as I kind of as the talk goes on. Okay, so that's also so that means that although a computation can be very long, the memory usage does not necessarily need to be linear to the computation. Okay, that's for ordinary program. And if we look at the circuit, there's also this kind of scenario. Okay, so let's say let's say if we have let's say we want to prove a statement, and the statement can be like represented as a circuit. Yeah, let's say a circuit like this. Draw a new one. So the circuit has a size which is C, but the amount of memory that we need to evaluate the circuit is often much smaller than C. I'm going to call it, let's say, M. Okay, so this value, the amount of memory that is needed to evaluate the circuit is often much smaller than the circuit itself. Okay, for example, it might just need it may not even need it probably just need like the width of the circuit or something. Okay, so this is much smaller than C. Okay, for example, why is that? It's mostly because like the circuit usually refers to some kind of computation, and in many cases computation, like the functions are reusable. For let's say, for example, there could be some of computation over here that involves a certain number of gate, and after the output is obtained, the gate in this block is no longer needed. So we do not need to store them. We can just forget about them, and then we compute the next bunch. And after the computation, we just need to remember the wire values because that's what matters for the next part of the computation. Okay, so because the circuit is often modular, after we finish the computation of one module, we do not need to remember all the internal wires of that module as long as that module is not used again. The wires in that module is not used again. Okay, so this means that there's often a very big gap between the circuit size and the amount of memory needed to evaluate the circuit. Okay, and so that's where this memory requirement comes into the picture. Okay, so ideally, it's always the case that whatever we want like the cost of zero knowledge proofs to be as close as possible to the cost of running the program or the statement or verify the statement in the clear. Okay, that's what we want. Okay, we want the execution of zero knowledge proofs to be as close to the insecure like plain text computation as possible. Okay, we want it to have as small communication as possible, as computation as fast as possible. We also want the memory requirement to be close to the like a plain text computation as much as possible. So ideally we would want the memory usage to be proportional to the circuit, to what is needed to evaluate the circuit, okay, which is M. Ideally, we wanted the memory usage to be linear to this, but most of the protocols, most of the protocols actually need memory that is linear to the circuit. Okay, so this is actually one of the biggest hurdle right now in many of the protocols. Okay, for example, let's say if you want to evaluate a billion size circuit, which is not that big actually, if we think about what's the logic it can represent, that a billion size circuit would require a lot of memory, not to mention like even larger ones. So as the circuit goes larger, you need like larger memories. Okay, like a terabyte of memory is not unheard of. Okay, so this is the classification of all different types of zero knowledge proofs. Okay, so in terms of attention, well, so the upper parts have been paid a lot of attention, while the lower part are paid much less attention compared to the first few points. Okay, so and also so there are also two settings of zero knowledge, which is related to the interactivity. Okay, on the first side, which is like a potentially asynchronous, it's potentially asynchronous in the sense that the prover may want to prove to a big set of parties in terms of the fact of in terms of the predicate f. Okay, so it means that the prover wants to prove to a big set of parties, and the prover after the prover compute the prover is going to go offline, and the set and other parties is going to verify it. For example, in most of the applications in blockchain space, this is how it is managed. Okay, but it's not always the case. Okay, there are also synchronous settings. Synchronous in the sense of when prover wants to prove to a verifier, the verifier and both prover and the verifier are online. So both of them are online at the same time. Okay, so both of them are online at the same time. So this would be like a synchronous setting. Okay, so ideally we want to get asynchronous, but asynchronous is also useful in multiple applications. Okay, even in the blockchain space. Okay. So what I will talk about today is a very different type of zero knowledge compared to existing ones. Okay, so first, on the drawback side, it is interactive, and it has a the size of the zero knowledge proof is often linear to the circuit size. Okay, so it's often linear to the circuit size, but not always. Okay. Although it's linear, the underlying constant is very small, so it only requires one field element per gate. Okay, and the constant is just one. It won't be like there's no constant in the asymptotics. When I say linear, the constant is one. Okay, so the communication could often be somewhat big. Okay, but on the other side, it is very efficient. Okay, so it requires only a constant number of AES operation. AES is the like a block cipher, and it can be accelerated using hardware AES NI. So this one is just like essentially like one AES is like a few cycles of computation in CPU. It also need a constant number of like field extension operations. With this one is also hardware accelerated. So there is also I think this is the one, yeah. So there's also a hardware instruction for this type of field extension operations. Okay, so essentially, so this kind of zero knowledge proofs requires essentially like a constant number of cycles per gate in terms of the CPU cost. Okay, so that's like a very nice. So the efficiency is like a very fast. Okay, and in terms of the memory, it is linear to what is needed to evaluate the circuit in the clear. Okay, it's not linear to the circuit size. It's only linear to the size that is needed to evaluate the circuit, which is what you need anyway, because in order to evaluate it, that's what you need. Okay, so it's also linear to that. Okay, and in terms of the security model, it doesn't need any trusted setup, and it can even be proven to be UC secure, which is a very strong notion in terms of composability of zero knowledge proofs. Okay, so I'm going to talk about this type of zero knowledge, and then I'll talk about because this kind of zero knowledge is very cheap in terms of the computation and memory, we can actually actually use it to build very large computation, very large like applications like proving like different kind of machine learning tasks on a very weak machine, and like run like networks like ResNet 101 and things like that. Okay. Yep. So I will talk about the first part, and so the first part will be on the zero knowledge proofs, and the last part will be on the machine learning applications. Okay. As I said, so this type of zero knowledge proofs is interactive, and it's many of the building blocks that it needs are also interactive. And the first one that we need is so-called information theoretic message authentication code, which is a protocol that is executed between the two parties. Okay, so this one was invented around 2011 and then 2012. Okay, so it first appears in like in the context, especially in the context of MPC and zero knowledge in 2011, 2012. So it's like roughly 10 years ago. Okay. So essentially, like so what it does is that so let's say if a prover has a value x, and then this kind of protocol is going to be able is going to generate two keys, m and k with this kind of requirement. Okay, so m has to equals to k times plus x times delta. So what does it mean? So it means that if x is 0, then the two values are the same, and if x is not 0, then like the two values has a difference of delta, where delta is only known to the verifier. Okay. So like so this is so we call it a information theoretic message authentication code because it allows the prover to do certain types of authentication, and it's information theoretic. Okay. So information theoretic just means that regardless of the computational power of these two parties, they cannot break where the authentication properties or other properties of this building block. Okay. So why this is a authentication? So first, from the value of kx, the verifier will not be able to figure out the value of x. Okay, so kx is independent of value x. Okay? And on the other hand, if a prover wants to convince the verifier that the prover holds x, then what prover can do is prover can just send m of x. Okay, because m of x. And because when verifier has m of x, the verifier can check whether this relationship holds. And if this relationship holds, then it has to be x. Okay. And if a prover wants to convince the verifier some other x prime, then like it's not going to check out because like if m equals to this, then m is not going to equal to the same equation with a different x prime. Okay. And if prover and the probability that the prover can find a mx that makes this equation hold is going to be negligible when the field size when the size of this element are large enough. Okay, so this is like what I mean over here in terms of how to open it. Okay, so essentially, so you can view like if you know the concept of commitment, then this is essentially interactive commitment. Okay, and if you don't understand the commitment, then you can just like think about it as a authentication. So like so there are too many symbols, so I'm just going to use a bracket to denote this type of authentication. So whenever I write a bracket of x, it means that the two parties hold some number of values such that they satisfy this relationship, and x means x over here. Okay. So this is like a very simple structure, and it has like a certain number of like good properties in addition to the fact that it is information theoretic. Okay, so first, it is additive homomorphic, meaning that like if we have this type of authentication on x and x prime, then the two parties can locally compute the summation of authentication of the summation of x and x prime, which I denote as x double prime. Okay, so the people like the two parties can do it by just locally compute their like m values and k values and sum them up, and that will constitute a new authentication on the sum of the two values. Okay, so this is very nice. Okay, so addition by a constant is also very easy. By like the verifier can just update the key value. Okay, and the multiplication by constant is also like is very easy. Where you can do addition, so you can multiply by constant. So there are ways to do it, and there are ways to do it fast. Okay, so this type of authentication was not very easy to generate before 2020. Okay, before 2020, this kind of authentication would require a high amount of communication. It's not very good. Okay, not very easy to generate. Okay, but since like 2018, 2020, like 2020, there has been a huge progress in a special type of protocol, with where the abbreviation is a PCG. Okay, so pseudo-random correlation generators. Okay, this is a very elegant idea that it actually produces a lot of interesting results. And one of the results is that it can actually generate this type of correlation, where in the context of PCG, it's also called a vector oblivious linear evaluation with very small cost. Okay, so for Boolean, the cost is like around like a 10 nanosecond. Okay, and for for large field, the cost is still like below 100 nanosecond. Okay, I think these numbers are probably already a little bit out of date because we've been improving our system implementation every day. So I think these two numbers are probably already out of date. Probably it's if you run the code now, it's probably much smaller than these two numbers. Okay, but anyway, so these two are very small. Okay, well, mostly because in order to obtain this type of information theoretic map, we do not need many public key operations. Okay, so we only need a very small number of public operations at the very beginning, and then all of the rest are just essentially just either non-cryptographic operation or just AES, which is a hardware accelerated, as I said before. Okay. Well, so all you need to know is that this type of authentication can be generated very, very efficiently. And in terms of the efficiency, we measure it in terms of nanosecond. Okay, so nanosecond like 2 minus 9 seconds. Okay, so we are working on a very efficient building blocks over here. Okay, so there are a lot of there are already 3-4 papers on this line of work in terms of how to make it powerful, how to make it efficient. But I for now I will you can just take it from here. Okay. Yeah, and yeah, so so here I talk about a field element because this is the prime or a field extension element. Okay, so you can also generate this type of wave vector OLE for integer rings. Okay, so you can also generate integer rings like integer modular 2 to the k, for example. Okay, there are actually two papers on this line of work now. So one is this work, and there's another work that is recently published in this year crypto. Okay. Okay, so now we know this type of interactive commitment or authentication. We can try to build a zero knowledge proof on top of it. Okay, and then we can build. After we build a way to compute the circuit, then we can talk about how how a machine learning protocol can be built on top of it. Okay. So in order to prove it in zero knowledge, so we first get a bunch of authentication, in the preprocessing phase. Okay, and then the prover is going to have the input omega, with some values. Okay, so what the prover do first is that the prover is going to send the difference to convert this random authentication to the authentication the prover needs, which corresponds to prover's witness. Okay, so yeah, let me probably draw a circuit just to make it clear. Yeah, so this would be WIs. Okay, so the input layer is going to be WIs. Okay, and what we do, so this is the first step, and what we need to do is to let the two parties obtain the authentication of the input wires. Okay, WIs. Okay, so we want we want the two parties to get authentication of the input wires on the first layer. Okay, so our goal is that we want to gradually get authentication of all the wires in the circuit and eventually get the authentication of the output wire in the circuit. And once we get the authentication of the output wire of the circuit, the prover can open this wire to the evaluator, to the verifier, and the verifier can check whether this value is is desired. Okay, so that's what we want to go with. We want to go gate by gate. Okay, and this is also why the memory usage can be small, because when we go to the next gate, let's say when we go to this gate, the authentication of the input wires is no longer needed, so we can throw them away. So we just need to store a small number of authentications as we evaluate the circuit. Okay, so this is the first step is just to get the authentication of the input wires. Okay, and after we get the authentication of the input wires, we want to every time we encounter a gate, we want to every time we encounter a gate, we always have the authentication of the input wires. We want to find a way to get the authentication of the output wires, okay, in some way. Okay, and we want to propagate this kind of action until the output wire. Okay, Also, there are two types of gate that we usually need to concern. One is the addition gate and one is the multiplication gate. Okay, because this type of authentication is additive, if we have the authentication of the input wires, then the authentication of the output wires is can be obtained directly by just like two-party locally like sum them up using the homomorphism property. Okay, so this one is easy. So the difficult part always come from the multiplication gate, where prover needs to, so the prover and verifier, so the prover is going to, both parties have the authentication of this and this, so this should actually be bracket. So we have authentication of the input wires, and we want to get the authentication of the output wires. Okay, so we also in zero-knowledge proofs, one thing is always true, and you should always remember it. That is verification is always is no more costly than computing it. Okay, so it's if you don't know how to compute it, you can always try to see whether you can verify it instead. Okay, so that's usually often very useful in terms of the construction of zero-knowledge proofs. Okay, and here we are also going to use this kind of idea. Okay, so we do not know the efficient way for prover to kind of for the two parties to compute the authentication of the output wires, but it's easy for the prover to kind of send a difference such that they can get the authentication of the output wires when the prover is honest. Okay, so if a prover is honest, then we can let the prover to authenticate the output wires just as input like any other input wires. Okay, but if a prover is not honest, then prover could could cheat, and if a prover cheat, then this value is no longer going to be correct. So we first let the high level idea is that we are going to first let the prover to specify what the output value is supposed to be, which prover knows because prover knows all the witness in the circuit. Okay, and after the prover obtain let the two party get the authentication of the output wire, we are going to run a checking process to check the correctness of this authentication. Okay, so we want to check this correctness of the authentication. Okay, so essentially, so if we abstract this question out, then it would be like we have, so after the prover send this authentication of the output wires, then the two parties is going to have so-called triplet, which is authentication of the two input wires and the authentication of the output wires. Okay, and if we have a large circuit with multiple AND gate or multiplication gate, then we will have multiple this type of triplet. Okay, so we'll have let's see, essentially we will have many this kind of triplet, and we want to check that all of them are correct. Okay. Also, I'm going to skip this slide because this is no longer the state of the art, and this is just kind of so in order to check this kind of triplet, where the first idea is to run a probabilistic game that can check the correctness. Okay, but this one is no longer the most efficient one. So so I'm not going to talk too much about it. But I guess all you need to know is that it's essentially, it doesn't really require any kind of complicated operation. You just need, all you need is to obtain this kind of efficient VOLE, which remember is on the order of tens of nanosecond to obtain each of them, and then you do some kind of a chip operation on top of them in a probabilistic way, and then you can check the correctness. Okay, but this is not the most efficient one, so I'm not going to talk too much about it. Okay, so instead I'm going to talk about a more efficient version of checking, which is a little bit more complicated, but if you pay attention, you should be able to follow. Okay. So essentially, so in this type of new type of checking for the zero knowledge proofs of multiplication gates. So we have two parties, so the prover has these values, and the verifier has these values. Okay, and we know that this relationship is satisfied. Well, this is the authentication relationship, and this is what we wanted to check. We want to check that the omega value satisfy the computation of a multiplication gate. Okay, so how to do that? We also from the verifier side, the verifier has case and delta. Okay, so we want the verifier to compute this value first. Okay, so this value can be computed by the verifier. Okay, And if we expand this out, we will get a bunch of stuff. Okay, so so why this equals to the right hand side? We also because we can replace Ka as MIA plus omega A times delta. Okay, so this equals to M alpha plus omega alpha delta, M beta plus omega beta delta, and then minus M gamma plus omega gamma times delta times delta. Okay, I just replace this by K with this, B with this, and this by for the gamma. Okay, so this equals to this one, and then if you expand this term out, then you will get the first one. Okay, so there are this the left side is the multiplication of sum of two values, and the right side is not. So there are totally 6 terms. Okay, so there are 4 terms on this side, and there are 2 terms on this side. That corresponds to 1, 2, 3, 4, 5, 6 terms in the equation. Okay, so this is how we get the right hand side. Okay, and after we get the right hand side, so we can observe that so there is some term that is known to the prover. This term is also known to the prover, and this is delta, is known to the verifier. And this term, oh sorry, this should be alpha, this should be beta, and this should be gamma. Okay, so this term is supposed to be 0. Okay, so where this term comes from? Well, so there is a delta here, there's a delta here, so it will give us omega alpha, omega beta, delta squared. And there is a delta squared here, so which is minus omega gamma delta squared. Okay, this term is supposed to be 0 if the relationship holds. Okay, if this relationship holds, then the omega alpha times omega beta minus omega gamma is going to be 0. Okay, so this means that this term is supposed to be 0. So it also means that if we want to check the AND gate, we just wanted to check whether this equation is a linear equation, okay, with respect to delta. Okay, so if we view delta as a variable, then this can be viewed as either a degree 2 polynomial or a degree 1 polynomial. Okay. So if the computation, if the circuit the circuit is computed correctly, then it should be a degree 2 polynomial. If the circuit is computed not correctly, then sorry, if the circuit is computed correctly, then it will be a degree 1 polynomial. So because this term will be cancelled out. Okay. Yeah. So now it's really okay. Yeah. So this idea is originally from a paper called line point ZK. Okay. Also a very recent work. Okay. So by this, essentially we want remember that previously, so we're talking about, so we authenticate the input, and then we let the prover to specify the wire values in an authenticated way, and then we want to check all of them. Okay, and now we reduce the problem of checking the gate to a problem of checking the degree of polynomials. Okay, and this is a easy task. Okay, how to check the degree of the polynomial. We can just we can first construct a linear equation which is of degree 1, and then we can just output the summation of this to the relationship that we want to check and the random linear equation that we come up. Okay, I mean, so this is because if you have a degree 1 polynomial and you add another degree 1 polynomial, it's still going to be degree 1. Okay, but if you have a degree 2 polynomial and you add a degree 1 polynomial, then the result will not going to be degree 1. So you can but the sum of them is not going to contain any information, sensitive information. Okay, so here some of the information can be sensitive, but if we masquerade it with a random degree 1 polynomial, then the result can be opened. Okay, that's why so that's how we reduce the problem of checking degree 1 polynomial to to a much simpler task. We just need to construct a degree 1 polynomial which can be done efficiently. Okay, so by this we can check the polynomial. We can check the degrees. Okay. Yep. But we do not want to just run this process for every gate. That's going to be too costly. Okay, so instead, what we do is that so we are going to compute. Let's say we are going to compute a constraint for each of the gate. Okay, and all of them should be degree 1 polynomials, or linear linear relationships. Okay, and we could check each of them one by one, but we can also run a linear combination of all of them and check them all together. Okay, that's also possible. So by running a linear combination of all the gates, the communication of checking is essentially a diminished. It's like a amortized to almost essentially negligible cost. Okay, so this is going to check is to reduce the cost of all of them to a very small. Okay, so in the end, so most of the cost of this protocol is here, where the prover needs to let the verifier know the wire values. Okay. And also because how it is computed by and gate by AND gate, it's the memory usage is actually very small. Okay, and you can see throughout all this kind of discussion, we never use any public key operations, and all of them are just basic operations like a multiplication, like a summation, like a subtraction, and things like that. So it's very efficient when we implement it on a common hardware. Okay, so here are some. Well, so this one is the old generation, so it doesn't so this one is the slower one. So this one is probably the more interesting one. Okay. And the numbers are already kind of out of date because I'm pretty sure this is below 50 nanosecond now. Okay, so even on a very small and even with even smaller a machine, actually I think I probably have it next. Yeah, I have it on the next slide, so it's fine. Okay. So it's so normally it's it's around it's on the orders of hundreds of nanoseconds in terms of the computation of each gate. Okay, so it's actually can be very efficient. Okay, and we also push the affordability to the of this type of zero knowledge proofs to the extreme. Okay, so these are the smallest AWS instance that doesn't have a burst performance. So it will give a constant ratio of performance. Okay. And for example, first one is ARM, which is the most economic one. And for this one, we can still compute roughly 5 million gate per second. Okay. And so for all of these machines, I think they have 1 GB memory. Okay, so they have 1 GB of memory. And well, I think most of them are a few cents per hour. Okay, so it's very cheap. It's the cheapest machine that you can get that can run some computation for a sustainable amount of time. Okay, so for Boolean circuit, then it's and with the cheapest with the most economic machine, then it would be being able to compute 10 billion gate per US cent. Okay, well, there are inflation, but it's roughly 10 billion gate per US cent. Okay, so it's very cheap. Okay, so even if we have a very large computation, we can prove in zero knowledge with very small monetary cost. Okay, even for arithmetic circuit, it's still very good. Okay, so billions of gate per US cent. It's essentially everybody has is able to afford to use zero knowledge proof to prove something to other people. Okay. Well, and I also I often it's not very easy to kind of understand exactly what does it mean. Okay. So usually so let me just use the cost of a granny-sized cup a latte as a Starbucks latte as an example. Okay, so if we use that as unit in terms of the cost, and then one cup of coffee is actually one cup of latte is going to be able to buy you this number of gate, which is 3,000 billion gates of zero knowledge proofs with 1 cup of coffee. Okay, so this is a kind of the type of affordability. Okay, and so in the end, the affordability essentially boils down to the fact that we do not need high memory, and that the computation is fast. Okay, so this is how we can actually bring it to be so cheap in terms of the cost. Okay. Yep. So there are also like some other optimizations. For example, like so I was talking about for example, let's say like one common task that people usually use to compare the performance is like a matrix multiplication. Okay, so this contains 10 to the power of 9 number of multiplication gate. Okay, so for the version that I talked above, it requires roughly 300 gig of computation with like 8 GB of communication. Okay, so it's not memory, it's communication. Okay, but actually it's like there is a optimization which allows you to do matrix multiplication even faster with even better communication. Okay, so like for example, like these are like I didn't mention them, but this is like non-interactive and succinct. So our proof size is not as good, but we can actually compute much faster, and we can use much less memory to compute the same task. Okay, we just need 1 GB. While like if we use like the non-interactive ones with small memory, that would need small communication, that would need hundreds of gigabytes of memory. Okay, so I guess this is where you can see the trade-off. Okay, so you can either get very small communication, but requires like a relatively longer time and longer approval time and like high memory, or you can get it down to like I guess like this is roughly 1,000 times larger, but the execution is much faster, and you only need like a much smaller machine, so everybody's machine can run it. Okay, this is kind of the trade-off. Okay, and also our protocol is interactive. Okay, so this is also interactive, while this is non-interactive. Okay, so this is the type of trade-off that we are looking at. Okay, and so this communication reduction is why I'm saying that it's often linear time, and it's at most 1 field element per gate, because in many cases, in some cases, like it can actually be better. Okay, so like and there are actually like many works like this line of zero knowledge proofs is improving like very fast in the past few years in academia, and we have like I think even this year we have like not just me but the community produced like 4 or 5 papers that pioneers like in terms of how to reduce the communication. Okay, so I won't talk too much about I guess if I have time, yeah, maybe I can talk a little bit about how this how the communication is reduced. I will talk about one type of approach where the communication could be reduced to an even smaller chunk, and then we'll talk about some other works that has been going on by the community in the past few, actually in the past year. So over here, when I talk about where is it? So over here, when I talk about the zero knowledge proofs, I implicitly assume that the computation is going to be represented as a circuit. Okay. I mean, like so cryptographers always like circuit because circuit has like a very small number of basic building blocks. Okay, so you can use basic building blocks and to build arbitrary things that you like. Okay, but the circuit also means that we need to decompose the computation into the finest the level in terms of the building block. So that might not be the best. Okay, so oh yeah. So instead, so over here, so in order to reduce the communication, so we know that like these are essentially the best we can hope for. Okay, and this one, the interactivity is it seems not very easy to overcome, but we want first the communication to be smaller. Okay, we want to bring down the communication as much as possible. Okay, and in order to bring down the communication, we don't want to represent the circuit as gate anymore. Okay, we want to represent the circuit as a slightly larger gadget. Okay, and this gadget could be, for example, a computation of a polynomial. That would be one example. Okay, so what it means is that, let's say there in the circuit there could be some binary gate, but there could be for example, there could be a larger gate that compute a polynomial on the input. Okay, so input is a vector, and it compute a polynomial on top of the input and output something. Okay, and when we encounter this type of polynomial, we will not break it further into gates. We want to compute this polynomial as a whole. Okay, that's the idea. Okay, and it just turns out that if we have like many different kind of polynomials, we can actually prove polynomials even like much faster than proving the polynomial by decomposing it into a small number of gates and prove them one by one. And also in terms of the communication. Okay, so essentially, let's say if we have multiple number, so essentially in the end, the communication is only linear to the highest degree of the polynomial. Even if we have many polynomials, the communication does not depend on the number of polynomials, but only the degree of the highest degree of the polynomials of all the polynomials in the circuit. Okay, so this is like very nice. Okay, because like you can see that here, like this bound is independent of t, so that's that's great. Yeah. So how it is done? So it goes back to the equation. This is a little bit complicated. Oh, there's a question or something. Oh yeah. So the implementation of the inner so there is a equation. This equation is the equation that I used that I mentioned in the previous few slides when I talk about a multiplication gate. Okay, and in terms of the inner product, we're just going to extend this equation a little bit more. Okay, so on the left hand side, instead of computing this simple operation, we are going to compute a slightly more complicated operation where where f is the statement, but is the polynomial. But instead of proving this kind of polynomial on top of the the input, we are going to compute it on top of the keys. Okay, and we also it's actually it's a little bit too complicated, but so maybe I will not go into the details exactly how it works. But so we have some explanation in our paper. So essentially, the idea is that even if it is the inner product, we can also convert the task of proving inner product into a similar task of proving the degree, checking the degree of the polynomial. Okay, so so in the end, it's going if the inner product is computed correctly, we are still looking at the degree of how to check the degree of the polynomial, which we already know how to do. Okay, so this is why this can be done in a similar way. Okay, and not only that, we can this is for inner product, and even if we have a degree d polynomial, there's also a similar way. But now instead of checking degree instead of checking whether the degree of the polynomial is 1, we are checking if the degree of the polynomial is d. That's where the cost, the linear to d, comes from. But otherwise, it's pretty much just the same. Okay. Yep. So essentially, let's say if we have multiple polynomials where so we have 5 input wires, 3 output wires, and 3 polynomials, and then the cost is going to be linear to not 3 polynomials. The highest degree is 5. Then the cost is essentially linear to the number of input, the number of output, and the highest degree of all the polynomials. Okay, so even if we have many more polynomials, the communication is independent to the number of polynomials. So this would mean that there are there are many of the statements that we want to prove in zero knowledge. We can represent by them into polynomials and get much better performance. Okay. Yeah, there are a lot more works in terms of how to make it faster. For example, there is a recent work to appear very soon this November in CCS, which is a more efficient version where they can actually prove in zero knowledge with half of the cost. Okay, so they can prove in 0.5 field element per gate rather than 1 field element per gate that I mentioned. Okay, but this is a little bit more complicated. Okay. There's also a work that is done in collaboration with members of LatticeX Foundation, where we can actually bring down this type of zero knowledge to sublinear communication when the computation for different types of circuits. Okay, and in the end, there are the researchers in in Europe, they also have some recent works where they can do they can follow this kind of paradigm and compute on integers more efficiently. Okay, so hopefully by now you should have a very some kind of idea how this type of interactive proof works. Okay. Oh yeah, I forgot to mention. Okay, so for this type, they're for this part so Kyle mentioned that the front end is open source, the back end is also open source, and when in order to run it, you need to get both part of the code. So everything is open source, and you all of you can kind of grab the code and try to run it on your side, and you can play with it with different type of task that you need. Okay, and here I want to talk about a particular type of application, which is where the main goal of here, which is the machine learning tasks. Okay. And in order to introduce why we wanted to kind of why we need zero knowledge proofs on top of machine learning, let me use a kind of an example. Okay, so we all know that let's say we have a model, we all know that okay, so the model can take, let's say, an image as input, and it can give you a classification of what this image is. Okay, so in this sense, model is just a special type of program. Okay, a model is nothing more than a program. Okay, it's just that it is a very special type of program in the sense that program also takes input and output something. Okay, so model only takes a specific type of input and the output specific type of information. Okay, so this is nothing more than that. Okay, and for program, we always know that program can have bugs in it. Okay, so let's say if we use specific type of input, it may make the program, it may cause, let's say, stack overflow or things like that. Right? So it could cause different kind of problems. And it's also the case for models. Okay, for example, there has been a long line of work. For example, if you add a dot in the blender, it may be classified to something else completely different. Okay, so this is so-called evasion attacks. Okay, so essentially you can, by modifying the image a little bit, you can actually prove it to a completely different stuff. Okay, so this has been proven to be very valuable. And for programs, we know that there are bug bounty program, bug bounty programs where if you find a bug in the program, you can kind of submit the bug to, let's say, one of the companies, and they will kind of pay you back because you find a bug for them. Okay, and for models, it would be similar. Evasion attacks can be viewed. You can think about it as some kind of bug in the model. Okay, so now the challenger, let's say a challenger find a particular type of input that can cause this kind of evasion attack. Okay, so what the challenger is going to do? Okay, well, the challenger could kind of send the tricked image to the model developer. Okay, and I think I have a, do I have that? I don't have that. So challenger could send a tricked image to the model developer and tell them, okay, see, I have the image, and and please reward me because I found a bug in your model. Okay, but the model developer, in order for the model developer to be convinced that the challenger actually indeed have the bug, then the challenger has to send the image to the model developer. But if the model developer knows the image, then model developer can essentially refuse to pay, because now I already see your image, I already know your bug. Why I do want to pay? I don't need to pay. Okay. So the model developer can essentially refuse, or the model developer can say that, oh, I already found this bug, so we already found it, so you are not helping us. So there are different kind of it could lead to different kind of dispute. Okay, but on the other hand, the model developer that is not going to pay the challenger before the challenger actually before the challenger show that the challenger can find the bug. Okay, so this is kind of a classical setting of trust when in the context of machine learning. Okay, and this is also a case where zero knowledge proof can help, because essentially the challenger just wanted to prove to the model developer that the challenger knows the image that can lead to the misclassification. Okay, the challenger just need to demonstrate the knowledge, demonstrate the ownership of the knowledge without revealing the knowledge. Okay, that's what zero knowledge proof of knowledge allows these two parties to do, and that's why like the zero knowledge proofs in machine learning could actually have many different kind of applications. Okay, here we're only talking about the inference. Okay, so and for inference is actually a little bit complicated, but like it's like a here like we are talking about like deep neural net, so it actually contains all different kind of stuff. And when it is like integrated with like zero knowledge, it has more like much more details. Okay, but in general, like there are two types of like computations in like a neural net. Okay, we have linear layer, we have nonlinear layers. And like for the nonlinear layers, like many of the operations are actually computed in floating point. Okay, and for linear layers, they are not. They are they are also computed in floating point, but like it's like much easier to handle. Okay, so so the system that we built allows you to use a existing model directly in, and you can directly plug in a existing model trained by somebody else, and you can directly plug that into our system to use. That's because we actually emulate all the operations faithfully in the neural net. Okay, because our zero knowledge is very fast, we actually emulate all the operations faithfully as if they are how they are run on terms of ordinary computers. Okay, for example, we support the standard IEEE 765 standard for computing the floating point when we do the all different kind of linear layers, for example, batch normalization, for example, sigmod, and softmax. All of the operations are actually done faithfully to ensure that we actually get the highest level of accuracy. Okay, and it also, in order to make it as fast as possible, we also designed some kind of customized protocols that can actually can do like for example, matrix proof of matrix multiplication much more efficiently. Okay, so all of them so we implement them as like a basic building blocks, and then we hook them up with like a Rosetta by some kind of intermediate interaction between these two parts. Okay, and we also in order to make it useful, we also provide some kind of connections between public commitment and the kind of authentication that we need in our zero knowledge proofs. Okay, so now so I'm going to talk about this how some details about this, and with that, now the challenger can essentially prove that okay, so challenger has like a special type of noise, and by feeding this special type of noise, let's say a public image is going to be it's classified to something completely different. Okay, and we can, for example, we can also prove that this noise has a very small norm, so it's a very slight perturbation on top of the image. Okay, so all of this can now be proven easily with this type of system, because this is essentially generic. You can prove any type of neural nets with different kind of structures, and you can kind of because the input is authenticated, you can also prove in conjunction with other different kind of predicate. Okay, for example, you can prove that the images are close to some public image. You can prove that the images are close to each other and things like that. Okay. Okay. So as I said here, so we need some kind of conversion between arithmetic and the Boolean, and this kind of conversion is used to connect linear layers and non-linear layers. Okay, so why is that? This is because so like we cannot really do zero knowledge proofs on floating point directly, because floating point are where they are floating point, they are not really like structured algebra, like algebraic. They're not really like, they don't have algebraic structure. They are like they're just they're like specially designed for hardware in some sense. Okay, so we actually needed to represent all of the floating point operations in Boolean circuit. So all the floating operations in the nonlinear layers are represented as a Boolean circuit. Okay, for example, for example, we need exponentiation, which takes input as a floating point and output a floating point as the exponentiation of the input. And this is used to compute softmax. We also need to compute a sigmoid and ultimate kind of operations. All of them are represented in Boolean circuit, because this is the way that we know to compute floating like IEEE. like a standard of a floating point. Okay. On the other hand, the linear layers are not computed in Boolean circuit because like the linear layers are really just a summation and a multiplication. So this can be done much more efficiently if we represent them as a finite field element of with a large field. Okay, so this means that we also need to convert between these two types of representation. Okay, so after we are done with the linear layer, we get authentication of arithmetic element, but we want to convert them into authentication of a Boolean element. Okay. So this kind of a conversion is going to cause some kind of trouble because it's not clear how that can be done. Okay, so in order to do that, we actually come up with a zero knowledge version of ADA bit. ADA bit is so-called extended doubly authenticated bit. Okay, so the idea is that we want to come up with a random element R in let's say which is authenticated, and it's like a mod P, and also authentication of 0 up to 1, like so all the bits in R in Boolean. Okay, so this is in Boolean. These are authentications in Boolean. This is authentication in arithmetic, with the assurance that they are consistent. Okay, they are consistent in the sense that R0 up to RT is the binary representation of R. Okay, so this is something that is very important because once we have this, we can do the conversion easily by just revealing the difference. Okay, and in order to obtain this, it's going to be another like a story in terms of obtaining this. But the high level idea is that because we are jumping between different kind of field, this type it's actually not very easy to check the consistency. And in the end, we actually need to use the Wolverine type of a probabilistic argument in terms of to check this kind of a consistency. So we need to invent a probabilistic game, and the game is going to ensure that if the game succeeds, then all of them are consistent. Okay, so this is the way to get this type of ADA bit, and once we get the ADA bit, we can do the conversion. Okay, so we can see that actually this type of conversion is not cheap. It requires, it's like, let's say if we compute one AND gate, the computation of one AND gate is on the order of hundreds of nanoseconds or even smaller. Okay, but the conversion actually requires it's like at least 100 times slower than this type of than like unit gate, like AND gate or like multiplication gate. Okay, so conversion is much more complicated. Okay, so cost is also higher. But the good news is that we do not need that many of conversion. We only need to convert like whenever we go in and out of the nonlinear layers. Okay, this is where we need to do the conversion. Okay, and it just turns out that there are like a lot more costs inside of the linear layers and nonlinear layers that actually are heavier. Okay, so this is where we solved the first challenge, which is the conversion. Okay, so we also need to we also need to convert some kind of public commitment with the authentications. This is to allow some kind of this is to allow the convert. Let's say if we have a let's say if I have a model that is publicly committed so that everybody can access it. Let's say I can host the commitment on the bulletin board, and then I can still run the zero knowledge proofs, which each of the individuals with the insurance that all of them use the same image or the same model. Okay, that's why we need to use this kind of public commitment. Okay, so essentially we want to kind of all of them has access to this commitment, and they want to, and when they run the zero knowledge proofs, they will get a authentication of some value X. Okay, and they want to ensure, they want to have the guarantee that this authentication, which is between these two parties, is consistent with the public commitment that is published on some implementation of the bulletin board. Okay, so this could also be done using like all different type of ways, and in our protocol, so we essentially use some MPC friendly block ciphers. Let's see, friendly. Block ciphers to perform the commitment. Okay, so essentially, in order to commit to the input, you can essentially just publish a certain type of encryption of the input along with a committed keys that would allow the party that would allow a safe commitment. And this kind of commitment is also UC secure as long as the commitment is UC secure. So like everything is good. Okay. Yeah. So this would allow, for example, a party to commit to the model at the very beginning. Okay. And in the end, so all of this is like very complicated to implement. For example, all the neural net, all the network can have different kind of configuration, and even inside of one network, different layers have different kind of size. So like different size that could also lead to some kind of difficulties in terms of the engineering, because let's say if we change the model a little bit, then we need to change a lot in terms of the cryptographic implementation. So that's not very nice. And that's where Rosetta actually comes into the picture and make it a very nice, very easy to use. Okay, so essentially, so like in the cryptographic backend, we essentially just expose a set of operators. Okay, that can be called by the Rosetta. Okay, so this set of operators includes, for example, matrix multiplication, which is then used for convolution, zero knowledge proof of convolution. We also expose interface for like nonlinear layers, for example, zero knowledge proofs of RaLu, zero knowledge proofs of all the operators over here. Okay, and once we expose the operators that actually allows the cryptographic operations, then Rosetta can actually take the neural net and dynamically parse all these functions and call the appropriate interface in the cryptographic backend. Okay, that's how this chain how we actually allow a very friendly construction of the neural net without worrying too much about the underlying cryptographic backend. And and it's also very easy to tune in terms of different types of neural nets. Okay, and we also, these are some examples of execution. Okay, so over here we I talk about three types of tasks. Okay, so there could be a case where both the model and the image are private, only known to the prover, or it could also be the case where the model is public model is public, but the image is private. Okay, so they come with different kind of cost. Okay, so the most expensive and the most heavy one is the case where both the model and the image are private. This is kind of where we have a lot to hide. We need to hide the model and also the image. Okay, and in this case, let's say if for a 5-layer network, we can compute it in all of them can be computed in very using very small memory and a very small machine. Okay, and then for the net, it is a very small network. We actually need a very just a few seconds of computation. Okay, but for very complicated a network like ResNet, the ResNet 101 is this is a neural net with 101 layers. So this is this is on the order where how people what's being used in real life. Okay, and it has 100 layers and all different kind of nonlinear operations
人越听越少，现在就剩10几个人。
Yeah, and it has about 40 million parameters in the network. And for this one, it takes roughly 10 minutes of computation. Okay, so it's decently fast. And if when the model is when the model is public, then it requires even less cost. Okay, and if we look at the cost, the precise cost, actually, so most part of the cost is actually spent in batch normalization, and the rest of the part are this part is for nonlinear layer. This part is the cost of Rosetta. This is for the input, and this is for convolution. So so we have the decomposition is also pretty interesting, because the batch normalization, the part related to batch normalization, can actually be avoided. So if we with some optimization, the batch normalization, because in inference, the normalization is not really needed, because the parameters are already trained already. So this part can actually be get rid of easily. and that would actually like even like reduce the cost even further. Yeah, okay. That's all that I prepared. Yeah. Thanks.
Anyone have questions about this session? Because most of our audience is based maybe a China background, so you can have any question in English or Mandarin is both okay. Because Professor Wang Xiao can speak Mandarin and English. 所以大家如果有问题用中文提问也是可以的，用英文都是可以的，我们都可以相应的回答。
大家不用不好意思，大家都随便可以提问，或者比如说有那个如果大家不好意思的话，我们可以把 recording 关了之后，然后再那个。
而且我们 recording 是有剪辑的，都可以了。
I see
哎，汪轩老师，我有个问题，我先来发问吧，就是说，我理解像在 ZK 的 machine learning 其实解决两个问题嘛，一个是说privacy 的问题，另外一个是VC 的问题，可验证问题。在解决 privacy 问题的时候，其实我也看到说行业有很多的解决方案，比如说用两方的 NPC，或者说用同态的方式。这三种 ZK 还有 NPC 还有同态的方式，目前大家有一个类似这样的研究的结合点，或者说相互的一个对比嘛？哪种方式会在目前会更能够用在生产系统里面？
那我就用中文回答了。
OK，
对，然后那个就是首先 zero knowledge 和那个就是首先 zero knowledge 那个可能和 MPC FHE 呢可能应该把它分开看。为什么呢？因为就是如果一个 setting 需要用 zero knowledge 的话，那么一般来说就是只有一方有private input， 就是 zero knowledge 就是如果两方都有 private input 的话，那么 zero knowledge 至少单独只用 zero knowledge 那肯定是不够的。所以就是如果比如说有一个 setting 只有一方有 zero knowledge， 只有一方有 input， 那么可能那个只有一方需要 provide 需要 protect privacy， 那可能确实是需要那个 zero knowledge proof。然后呢，这是一方面，另一方面呢就是那个一般来说 zero knowledge proof 呢都是用 malicious security， 就是就是单方有 input malicious security， 那么就是 zero knowledge proof。然后 MPC 的话它就比较广了 ，MPC 就是如果我们真的 classify 的话，你可以把那个 zero knowledge proof 当成是一个 special type of MPC，where only one party have input。就是如果不考虑这个 special type 的话，那么一般来说 MPC 的话是需要那个至少有两方有 private input， 就是两方有 private input， 两方以上有 private input 的话，这时候比如有 two party computation 或 multi party computation， 它就 make sense 了。然后呢，在这个情况下的话，它也分就是 semi honest 和 malicious。它的 cost 也都不太一样，然后 FHE 的话，我觉得你就可能就是你可以把它当成是那个实现那个就是它可能更多的那个是一个那个 tool 吧，就是它可以拿来做一些，它可以就是 FHE 也是可以拿来实现 zero knowledge proof 的，也可以拿来实现那个 MPC 的，它就是 FHE 的。那个就是它原来那个就最开始的那个 designated 的 application 呢是 outsourced 的 computation， 对吧？就是比如说我有一个计算，我可以把我的数据先加密之后发给 server 呢在上面做 homomorphic operation， 然后呢做完结果之后再发给我就可以直接解密出结果。但是就是这个 outsource 这个 setting 呢，那个就是这种 outsource 的 setting， 那个就是大家做的不太多了，大家更多的是就是把 FHE 当成一个 building block 去实现那个一些特殊的ZK 或者那个 MPC 的一些特殊的一些东西。然后至于那个对，可能这个场景可能就是大概是这么一个情况。
别的同学还有问题吗？因为我们看线上还有不少同学在听课，看大家，因为我是觉得，大家可能对于纯粹的 ZK Gross 16啊，或者 Stack 啊，或者大家 Hard Tool 会听的比较多，在行业内，比如说用 ZK 做大规模电路的这个推理，或者大规模电路，甚至其实做的还是比较少的。我们今天请汪潇老师过来，也是 从另外一个侧面去 prove，就是 ZK 如果在一些比较大的这种门线的情况下面，如何去做这种优化的方式。其实 interactive 就是一个思路，因为反而在 Web3的 industry 里面，大家更熟的是 non-interactive，比如说 ZK Snack 啊这些算法，大家都研究比较多。反而这种interactive 的被大家可能忽略了。今天也是把它反过来拉起来看，说对比一下，interactive 这种 ZK 其实也是有它一些特殊的场景在里面的，包括在 AI 的领域，都是有不错的。然后我们也是把刚刚我也在那个 message 里面把我们的 Rosetta 框架发给大家了。我们除了实现这种 ZK 的方式，包括用 NPC 去做 ZK，也是从这几年大家研究比较多的一些思路，包括其实看看汪潇老师这张图也能看出来，在整个 AI 里面分了这种线性的计算，还有非线性计算，所以拆分起来，比如说用布尔电路啊，或者用算术电路啊，做这种精确的优化呀，像传统的 ABI3 啊，或者说Secure 的 NN 这种算法都很多了，大家可以借着我们的开源框架再看一看，拓展一下大家对于privacy 的这种设计的思路，也是一个不错的一个切入点。所以呢，今天也是辛苦王湘老师给我们讲了很长时间的这个协议的设计细节啊。我们刚好又把那个开源框架回头我们再 share 在我们的 group 里面，大家可以结合着代码，再反过来把汪湘老师这篇论文再看一看，因为我们是有 paper 做背书的。如果有问题，我们可以再提问。就看现在还有同学有问题吗？如果没有问题，我们今天的 session 就先结束了。
哎，这里好像有一个问题，有没有比较基础的论文推荐？这个同学的现在的背景是什么样的？就是你如果跟我说一下你现在的背景，我可能比较容易就是推荐，因为这个不同的背景可能推荐不同的论文可能比较合适。就是那个你大概是就是了解嗯。如果就是如果你比如说你对 zero knowledge proof 比较的了解的话，你也许那个可以就是直接看这个论文。其实你直接看我们合作的这个论文应该就差不多了。它里面有一些那个它里面基础的一些 background 的介绍都是有的。但是如果那个你只是了解只是说了解这个 zero knowledge proof 的定义。并不知道它内部就是没有接触过一些里面的一些就是 protocol 的 design 的话，那你可能需要比如说可以先看一下那个你可以先看一下我老板的教科书 Introduction to Modern Cryptography 如果密码学知识比较就是需要先补一些密码学知识，可以先看一下那个可以先稍微那个就是夯实一下基础，然后可能会好一些，因为这些论文它经常都是，它会跳过很多基础的东西，可以比如说看一下那个就是找一本那个东西，那本里面可能比如说会说到，比如说什么 random oracle 呀各种东西，它都会就是介绍一下，然后的话可能会看论文可能会好一些。哦，你是说哦，那我觉得你直接看应该问题就不大。那如果你这个的话，那你可能比如说直接看一下，直接看那篇 paper 或者那篇 paper cite 的几个那个 prior work，应该你是做 crypto 那就不用的，那你直接看就行，那你应该没问题。ZKP 和 OJ，呃呃，对，其实对这个是 good point，就是为什么是个 good point 呢？因为我们在就是在这个卡尔发的那个 ePrint 的 link 里呢，我们就是也提到了一个类似于 online judge 的一个 application，但是呢，我们提的呢是 ML 的 competition 的 online judge，就是说我们当时那个情况呢是说，OK，比如说那个我们这个要把 model 发给，就是我们比如说就是那种 ML 的 competition，比如说那种什么。都是说，比如说我算好了 model 之后，我把 model 交上去，然后他一天给你 classify 一次，然后呢，他再告诉你结果，然后呢，你第二天你每天比如说都可以 classify 若干次， 然后呢，你还必须要保证你不会就是开假的账号这种情况。然后呢，这里就可以，比如说你就可以用那个 zero knowledge proof 那个去代替那部分。对，这个就相当于 online judge 可能就相当于是一个更加 general 的一个东西。对对对。我们那个 paper 我看一下那个我们 paper 里面那个写了3个 application， 这个可能这个可能就相当于有点类似于我们 paper 第2面的第3个 application。
好呀，如果没有更多问题的话，那我们今天的这个 session 就到此，然后回头我们把这个 paper 还有我们实现的 code，发到我们群里面去，大家可以再看一看，如果有问题，我们可以到时候再一起讨论一下，好吧
对对对对，然后有什么问题我也可以随时解答的。对，
？OK，
大家一
so
起
thanks
一起
for
把它 develop 起来。
好呀，那我们就结束吧，然后谢谢王潇老师的时间。
哦，没有没有没有，谢谢大家。